We now discuss the solution of a problem from the section Complex Analysis, and the problem is on the concept of entire function. This problem has appeared in CSIR National Eligibility Test held on 30th November 2020, and it is from the section B. The problem is, let f, g be entire functions such that limit z tends to infinity of f of z by z to the power of n is equal to limit z tends to infinity gz by z to the power of n is equal to 1 for some fixed positive integer n. Which of the following statements is true? Options. The first option is f is equal to g. Option 2. F minus g is necessarily a polynomial of degree at most n minus 1. Option 3. There exists f, g with these properties such that f minus g is a polynomial of degree n. Option 4. There exists f, g with these properties such that f minus g is not a polynomial. We now discuss the solution of the problem in detail. We are given two entire functions f and g, and we are also given limit z tends to infinity f of z by z to the power of n is equal to limit z tends to infinity g of z by z to the power of n is equal to 1 for some fixed positive integer n. Let's first of all take limit z tends to infinity f of z by z to the power of n is equal to 1. Now replace z by 1 by z in this. Then the limit becomes limit z tends to 0 of f of 1 by z by 1 by z to the power of n is equal to 1. This will imply limit z tends to 0 z power n into f of 1 by z is equal to 1, which is not equal to 0. Then f of 1 by z has a pole of order n at z is equal to 0. f of 1 by z has a pole of order n at z is equal to 0. Coming back to z is equal to infinity, this will imply f of z has a pole of order n at z is equal to infinity. We now recall a theorem. That theorem says an entire function has a pole of order m at infinity if and only if it is a polynomial of degree m. Now f of z has a pole of order n at z is equal to infinity. By this result, f of z is a polynomial of degree n. Now let us suppose f of z is equal to a n z power n plus a n minus 1 into z to the power of n minus 1 plus so on and so forth plus a1z plus a0, where an, the leading coefficient, not equal to 0. We continue in the next slide. This is what we have from the previous slide. Now f of z is a polynomial of degree n and f of z is a polynomial like this where an not equal to 0. Let's take this limit z tends to infinity of f of z by z to the power of n is equal to 1. Let's take that and divide f of z by z to the power of n, then take the limit as z tends to infinity. Limit z tends to infinity, after the division it will be an plus an minus 1 into 1 by z plus so on and so forth plus a1 into 1 by z to the power of n minus 1 plus a naught into 1 by z to the power of n is equal to 1. Limit z tends to infinity of 1 by z is 0, 1 by z to the power of n minus 1 is 0, 1 by z to the power of n as limit z tends to infinity will be 0. We are left with, after taking the limit, it is only an on the left hand side. An is equal to 1. So thus f of z will be z to the power of n, because an is equal to 1, plus an minus 1 into z to the power of n minus 1 plus so on and so forth, plus a1z plus a naught. That is, f of z is a monic polynomial of degree n. And similarly, arguing for limit z tends to gz by z to the power of n is equal to 1, we obtain g of z is a monic polynomial of degree n. Let us say that is equal to z to the power of n plus bn minus 1 into z to the power of n minus 1 plus etc. plus b1z plus p naught. Let's go for the options. Option 1. So, if this is the case, can it be f is equal to g? It cannot be, because there is no guarantee that an minus 1 must be equal to bn minus 1. Not only that, all the coefficients must be equal. There is no guarantee for that. So therefore, f not equal to z, f not equal to g. Yes. Now, let f of z is equal to, let's give a counter example. F of z is equal to z, g of z is equal to z plus 1. Now, we see both these functions f of z and g of z satisfies the given properties, these two properties, for n is equal to 1, but f not equal to g. Hence, the option 1 is not true. Let's continue in the next slide. So, f of z is a monic polynomial, g of z is a monic polynomial like this. Now, let us take f minus g. And now, fz minus gz will be z power n cancels, and we are left an minus 1 minus bn minus 1 into z to the power of n minus 1 plus so on and so forth, plus a1 minus b1 into z plus a naught minus b naught. So, this is the f of z minus g of z. So, f is a polynomial, g of z is a polynomial, f of z minus g of z is also a polynomial. And the degree of this polynomial is n minus 1, provided the coefficient of z to the power of n minus 1 is not equal to 0. That is, a n minus 1 minus bn minus 1 not equal to 0. Otherwise, if it is equal to 0, its degree will be less than n minus 1. So, therefore, f of z minus g of z is a polynomial of degree at most n minus 1. Thus, the option 2 is true. And let's look at the options. And in option 3, there exists f and g with these properties. F minus g is a polynomial of degree n. This is not. Why? F minus g is a polynomial of degree at most n minus 1. There is no guarantee that it will be of degree n. Not only the guarantee, it is polynomial of degree at most n minus 1. At most n minus 1. Therefore, this will not happen. And it is a polynomial of degree at most n minus 1. F minus g is not a polynomial. That option is not true. Thus, the options 3 and 4 are not true. So, finally, our answer is f minus g is necessarily a polynomial of degree at most n minus 1, and hence our answer is the option 2 is true. So, that is the problem from the complex analysis, and the problem is on entire functions, and I hope that you have understood the solution of this problem, and I wish you all the best. Thank you.